need to remove the vertex in such a way that you get disconnected graph. So remove the remove set of vertices so that, or in such a way that removal of that set produces a disconnected graph. Okay, provided that set should be the minimal choice. Okay, provided that the set should be of minimal choice. And what is the meaning of minimal choice? Already we discussed in previous video, so you can refer to that video. Now see, we'll consider example, and through that example we'll try to understand. So the same graph we'll be considering what we considered in last lecture. See here, these two, the same graph you can draw. They are connected with this. Here you have the vertices. For example, this is 1, this is 2, this is 3, 4, 5, 6, and the edges we can denote by A, B, C, D. Here you have E, F, G, H, I. Okay, so in this example, suppose this is example 1, the same example we considered in previous video. Now here we need to check whether this 5,3, check whether this is a cut set or not with respect to vertex. Okay, 5, 3. Now see, one interesting fact with this cut set with respect to vertex or vertices is that once you remove a vertex, then corresponding the adjacent edges will be removed. Okay, so this is one main important or you can say key point. Okay, that when you are removing a particular vertex, then the adjacent edges will be also removed. See, if you remove suppose 5 and 3, see 5 and 3 you are removing means this vertex you are removing, this vertex, see this vertex you are removing, and this vertex you are removing. So once you are removing 5 means adjacent edges, this one will be removed, this one will be removed, this and this will be also removed. Okay, and once you are removing 3 means corresponding to this and this one will be also removed. See, once we remove this, then what we are getting actually, see, follow this, 5 remove means 5 it is removed, as well as this part it is removed. Okay, alright. Now see, 3 removed means this part and this part also removed. So what we are getting? We are getting a disconnected graph. Okay, we are getting a disconnected graph. But is it minimal choice? Just think, is it minimal choice? What is your answer? See, if you are simply removing this 3, then see, already you had 5 here. Okay, once, see, 1 minute here, once you are removing this, see, 3 you are also removing, that means this is gone, this is also gone. Now see what you have, nothing here, nothing. So the remaining graph, this one it is a connected graph. So this 5 and 3, this is not a cut set with respect to vertex, because ultimately you are getting this part only, and which is a connected graph. Your target was to get a disconnected graph. This was the first target. So this is not a cut set because you are getting a connected graph. Now draw the same graph. We'll try with some other set. So this is your 5, this is 3, this is C, this is B, this is F, G, this is G, this is G, okay, this is H, and this is E. Okay, now suppose I am removing this 6. I am removing 6. Okay, suppose I am removing 6. So 6 removing means this part we are removing. So this part removing means you have to remove this edge also, because this is the adjacent edge. So ultimately you will have this part only, which is again a connected graph. So no question of being a cut set with respect to vertex. Okay, now if you remove suppose 5 and 2, 5 and 2, see where is that 5 and 2? See 5, you are removing 5 means all of this part, this and this will be removed, and 2 removed means this one and this one gone. Okay, so after removal of this 5 2, what you are getting exactly? See this part, this 5 removed means this and this gone. 2 removed means this gone along with this. Okay, gone. So only you will be having this 6 here, here 1, 4 and 3. So this is a disconnected graph. So it satisfies the first condition, that this removal of this set will give you a disconnected graph. But now check whether this is a minimal choice or not. Okay, see you are unnecessarily removing this 5, because if you just simply remove this 2, then what you have, see if you are removing 2, that means in that case you would have this one along with this, which is a disconnected graph. So simply if you are removing this singleton 2, then it becomes a disconnected graph. So why you are unnecessarily removing this 5? So this is not a cut set, because it is not minimal choice, okay, whereas this one it is a minimal choice and this is a cut set with respect to vertex. Okay, so this is how we check cut set with respect to vertex. Now just like our previous understanding where we discussed edge connectivity, here we have a term that is known as vertex connectivity. So vertex connectivity, it is, we'll go with the formal definition. What is vertex connectivity? So vertex connectivity, what is vertex connectivity? See, each cut set of a connected graph G consists of a certain number of vertices. Okay, the number of vertices in a smallest cut set, the number of vertices in smallest cut set with respect to, obviously with respect to vertex, is defined as vertex connectivity. Okay, and it is denoted by K of G. So in this previous example, if you consider here the vertex connectivity, so K of G in this example, suppose this graph it is G, so it is clearly visible this 2, it is the smallest cut set, so K of G value will be 1. Okay, K of G value it is 1. So if you simply remove 2, then you are getting a disconnected graph. Now see, if k of g, that is vertex connectivity, is 1, that implies that particular vertex, that means the set will have only one vertex, okay, for which you will get a disconnected graph if you remove that particular vertex. So that particular vertex in the smallest cut set is known as articulation point. Okay, so there may be question like that, find out the articulation point. Instead of giving direct question, they can ask you find out the articulation point. So in our previous example, the articulation point was what? 2 was our articulation point or articulation vertex. Okay, so in that example, now see, one important result you should know related to this vertex connectivity, edge connectivity, and degree. Okay, so this important relation you can write down as note. For different graphs you can verify this. K of g is less or equals to lambda of g is less or equals to minimum of all those degree of all the vertices. Okay, degree of all the vertices, v belongs to capital V, suppose. Okay, that means whatever, suppose g, this graph, it is v comma e, okay, set of all the vertices. So here see this relation, k of g, that is vertex connectivity, less than edge connectivity, less than minimum of all the degree, okay, of all the degree. That means whatever vertex you have, calculate the degree, the minimum one here, okay, which is satisfying this relation. So one can prove this result, but for the time being you can verify this result for different example. For example, this previous example you can take and verify this result. K of g you got. Now find out that edge connectivity, okay, and find out degree of each of these vertex and check whether you are getting this result or not. This is a task you can try by yourself. Okay, try to verify for example 1. Okay, and let me know whether you are getting this result or not in the comment section. Okay, thank you.